I will explain the method I teach my students, the three-step method, the OET method, the method of thinking defect. Listen, examine, and treat. Listen, examine, and treat. Let's contemplate here, let's proceed, and let's thoroughly analyze. The reduced DC voltage. Initially, what exactly is the DC voltage? The DC voltage is precisely 310 volts. Certainly. The direct current voltage is precisely 310 volts. Excellent. All right, I comprehend. Because there are several voltages on the board. AC voltage 220, DC voltage 310, DC voltage 15 volts, DC voltage 12 volts, DC voltage 5 volts. So which voltage is this error referring to? The DC voltage of the power capacitor, high DC voltage. Why? Because it is the only one that the board measures. The board measures both AC voltage and DC voltage. If he mentions that it is a DC voltage error and the sole DC voltage that the board measures is the 310 DC voltage, then make sure to take notes. What I'm imparting to you here is just a part of the various pieces of knowledge that I will be sharing throughout the lesson. So this is one. If it mentions rectification and DC voltage, the board only reads the DC voltage of 3.10V. It doesn't read any other DC voltage, okay? If you didn't know that, now you do. So take note, the board only reads the DC voltage. There are two possibilities for this error. Let's create a line of reasoning here. And first, listen. The OET method is to listen, examine, and treat. So please listen carefully. I attentively listened to the board and I detected the error. Now I shall formulate hypotheses. Our work at the bench is to formulate hypotheses and verify hypotheses, then later check the hypotheses. Check 23 DC link error. The DC link is restricted to solely DC link 310. Consequently, I have two possible scenarios. Either the DC link 310 is non-existent or the DC link 3108 is absent within the capacitor. Subsequently, the board is accurate. It will indicate the precise error, or it is low, correct? If it were not, it would not display an error. First thing, what do you mean, Londa? If the voltage doesn't drop, there's no voltage on the board, it won't turn on. If it doesn't turn on, it won't show an error on the condenser. And it'd cause a communication error on the evaporator unit. Clear so far? So it's turning on, but the voltage is too low. It is necessary for it to have 310 volts, 300 volts, 290 volts, 280 volts. It is capable of holding up to 260 volts, many of the machines. LG, certainly, if it is intended to be passive, it consistently maintains at a low voltage level like that. However, if it provides a direct current link and you proceed to measure, if it is at 250 volts, for instance, 240 volts, 180 volts, the board will activate and yet the board will display the error message. And it will be in the middle correctly, right? At the time, if it's this case, it could be a PTC in the circuit. It might be the PTC heating up, opening, and lowering the voltage. Maybe the PTC relay didn't remove the PTC from the circuit. It could also be a faulty power capacitor. It could potentially be a few different things. Alternatively, it might be that there is indeed voltage present. In my experience, the majority of cases tend to be like this. There is voltage. There are 310 volts present, which is correct. However, the machine stops working and shows a DC link error, indicating a DC voltage problem. The voltage supplied to the board isn't enough. When this particular situation arises, which is the second hypothesis I am presenting to you, when this situation takes place, you will need to thoroughly examine the circuit that is responsible for accurately reading the voltage. If the circuit board possesses 310 volts and you have measured it using your multimeter, observing 310 volts, and it is a substantial power capacitor with 310 volts, yet the board indicates it does not, it can solely be reading inaccurately. Did you observe? There is indeed voltage present. You observed the voltage, you measured the voltage, and yet the board is indicating that there isn't any voltage. Therefore, she is being misled. She is interpreting it incorrectly. To assert that the attention level is elevated or diminished, she must accurately read the attention. For the board to claim the attention is high or low, it must read the attention. Does it make sense? For the board to say the voltage is high or low, it must read the voltage. Therefore, it will assess the voltage, and evaluate it inaccurately. If it evaluates it inaccurately, it will consequently provide the error inaccurately. So she will have two hypotheses. These are the most common in these cases, okay? But I have the machine here that starts the compressor and gives the RD clink. If I reach 23, as soon as the compressor starts. When the compressor starts, the voltage drops, showing the error correctly. Measure when the compressor starts and the voltage will drop. You'll see it drop when the compressor starts. Then the error shows correctly. Make sense to you? Does this particular way of conceptualizing the defect make sense to you? That's precisely what you need to work on internally. It is applicable to electronics and it is relevant to any type of equipment. All right, let's start here. I'll begin first with this smaller board of the dual inverter, known as dual inverter. This is the capacitor you need to pay attention to. You generally access this board here, right? Flipped. So this one here, this voltage needs to be on this capacitor. You'll measure as the voltage scale goes down. Here it won't show anything. Carefully measure that it needs to be 310, 300, 290, 280, between 280 and 310. Between 280 and 310, work within this range, okay? Measured here, there's no attention or it's low. As I mentioned, if it's absent, the error won't show. It must be low. If it's low, the error will appear, and that's right. In this case, what could it be? What would I analyze? I would check if this component here is heating up. This component here is the PTC. I would check if it is heating up. If it is heating up, it's because this relay here didn't remove this PTC from the circuit. This relay didn't activate. If it did, it might be faulty. Could be the relay or the circuit activating it. All right? Could be the relay or the circuit activating it. If the PTC is heating, or if 220V is dropping, I check if 220V is dropping. If 220V is not dropping, it's not low. Therefore, the capacitor voltage should be high. If there are 209 here, 210V, 215V, the capacitor should have good voltage. If it doesn't, it's this little circuit here. You see, usually that's where the problem will be. There, under. As I mentioned, it's either the relay activation, or the PTC. It's usually not the PTC. It's generally the relay activation, the circuit that activates the relay. Here are the relay coils and the relay contact. Just follow the coils here and you'll see the circuit that activates it. What exactly are we planning to accomplish here? We need to thoroughly analyze this circuit. If not, and there is voltage present on the capacitor, yet the board is still displaying a communication error, then the power section is quite straightforward. Here's a relay and a PTC, it heated up. Check the relay and its activation circuit. See if there are 12 volts at the relay coil. How do you measure 12 volts at the relay coil? Set the DC voltage scale and place one probe here and the other probe here. Check if there are 12 volts. If there are 12 volts, this relay should be activated. Then check if it is activated here. I see what's the voltage here? AC, right? I see 220 is reaching the bridge. Anyway, V220, V310. If there is 220 and not 310, the 310 is low, the defect is around here. If there is no 220, the 220 is also low, the defect is in the network. It's a grounding that's on the neutral connected, which is wrong. It pulled. It was a grounding, not a neutral. Anyway, it's a problem in the electrical system. Lawhander, I saw that there are 310V here. Tell me that there are 310V, but the board says it's with DC link. What are you going to do? You will take this circuit board, rotate it here, and examine, search for the positive. Initially, the capacitor possesses a marking. This marking here signifies the negative terminal of the capacitor. The opposite side is the positive. There are two pins, correct? This one is the negative. When I turn the board here, this one is the negative and this one is the positive. So what am I going to take? The positive trace. Look at the positive trace here, man. It is quite an extensive trace. See, I will take the positive traces and search for any location where traces are emerging, correct? For some type of reading, all right? Some kind of reading. And subsequently, I proceed over here. Take a look. I will have it right here. Take a look. Pay close attention to this. This is the track, you see? This is the track right here. Observe. I have a jumper. I'll even demonstrate what a jumper is. I'll put its continuity here. A jumper from here to there. There's a jumper. It shows 0 ohms. See it? Is it functioning properly? Allow me to modify the angle on my multimeter. There. It's done. Outstanding. Completely flawless. It will be situated right here. This specific one reaches this point, arriving positively from the IPM, not at this location nor at that one, correct? There exists a capacitor located here, yet there is an additional output present here, and there is a jumper extending from this point to that point, correct? There exists a jumper extending from this point to that point, and subsequently I shall trace the path in this direction. Observe. I trace the path in this direction. Observe. A jumper arrives at this location. This particular one proceeds to the transformer coil, correct, to the transformer coil, which is what precisely? The coil of the transformer serves as the primary winding of the transformer. It receives the voltage from the capacitor to generate the primary winding of the transformer. This is a standard configuration of the switched mode power supply. But the circuit will also diverge at this point. Everything is an integral part of the power supply circuit, and indeed there is a resistor here that connects with this additional resistor. It arrives here, and in this additional resistor there is a capacitor, correct? There is a capacitor that ought to be connected to the ground, this capacitor, correct? Certainly. Oh no, skip the capacitor. There is a resistor here, another one here, over there. So there is one resistor, two resistors, three resistors, and the middle pin of this resistor leads a trace and comes here to a path over here. Let me see if I can find it here. Advance along this pathway, arrive at this specific point, traverse through a resistor, and continue onward to the microcontroller, from the resistor to the microcontroller, with 0 ohms of resistance. I shall apply additional pressure here for you to observe, utilize for logical purposes, positive connection here, positive, and pass a jumper wire at this location. Here is a resistor that connects from here to here. This point has another resistor that comes here. Here is another resistor that goes here. This is G and D, okay? Then this capacitor here, G and D. In this particular section, I am not conducting any further analysis, but I observe that precisely in this central area, if you pay attention right here, allow me to concentrate here, will it focus? It appears it will not. Right here, there's a trace coming out like this. This is the trajectory I pursued. Observe. It proceeds here to the yellow eye and continues onward. It might become obscured from your perspective, but it proceeds here to this specific point, to this particular pin here. This pin possesses a resistor extending from this location to that, and from here there's a capacitor leading to the ground, and it proceeds to the microcontroller. The microcontroller is short-circuited. This board here is a discarded board with a shorted microcontroller. Yet the logic here pertains to this circuit. What is the issue that could potentially exist within this circuit that would result in the reading error? Within this particular circuit that I have just demonstrated here, these components are the resistors. These components are indeed the resistors in this context. These particular resistors. Please continue following along here. It will be specifically this particular resistor, this specific resistor, and this particular resistor, correct? It's these three specific resistors. They will continue to proceed to transmit a reading, a sample of the voltage to the microcontroller. I observe it reaches the microcontroller, the path I followed. So the LiPair 310V drops this voltage across two high resistance resistors. And these two resistors, there will be a sample, for example. Okay, just got it, right? It's 310 volts. When there's 310 volts here, there will be 3.1 volts here. Let's suppose it drops by 100 times, right? It is 100 times smaller, so I have 310 volts here, and here it will have approximately 3.1 volts, for instance. This is merely an example, as I am not entirely certain of the precise value. I would need to verify the voltage map to confirm this. However, there will indeed be a voltage sample present here. This voltage sample will be transmitted to the microcontroller, and when the microcontroller reads this voltage, it will recognize that this voltage is indeed present. As this voltage is present, the board will read the voltage here in a proportional manner. Do you agree with me if any of these here change? Especially these two here in the reading. If any of them change, pay attention, if any of them change, will the reading arrive incorrectly at the microcontroller? So, when you take a circuit board equipped with the MD Clink CH23 on the LG, you guide me and there is electrical voltage present. The issue arises due to the voltage reading circuit being incorrect, alright? The voltage reading circuit is indeed incorrect. So, it is reading inaccurately. Generally speaking, it is either due to another open trace, a cold solder joint, or typically an altered resistor. As these are reading resistors, they are required to provide the correct value. They must deliver a precise value. Exactly. How many times have I encountered a defect? The defect was to replace the resistor. On the other board, the same logic. Let's move on to the other board here. For another LG model, you're already familiar with the signal, so I'll move faster now. You get the logic, right? Measure the voltage. The voltage level is low. Mega 220. It possesses 220. The voltage level is low. The problem will be with the PTC. The PTC will be here. See, if it is heating up, it could be the relay that didn't remove it from the circuit. Check this relay and the circuit that activated the relay. Look here. Relay, it triggered the relay, it triggered the relay. Now we turn it. This foot also, when the board is turned, sometimes I get lost too. There's a relay connector here, and here are the two pins of the relay coil. Check if there are 212 volts here at the relay and see if it closed the contact. All right. Now pay attention to the capacitor. What do you do next? Flip the board again. Let's go. This one is bigger, right? The capacitor is here. I'm looking for the positive. The positive here is this one, right? I shall examine along the positive trace to determine what component reads this particular signal. Here is the capacitor and here is the transformer coil. Additionally, here is another capacitor and here is the resistor. However, it is the resistor of the primary circuit. So the signal isn't here, it's not here. I'll go this way. There's a jumper here. It originates from the builder bridge, not precisely in this location. There's a jumper situated right here. Oh, it's not even a jumper. It has already transitioned into a resistor specifically identified as R01Y. There's a resistor located here, and there's another resistor positioned over here. This particular track, if I trace it, leads to this point and then proceeds to that location. Here, it halts, which is not what I desire. It comes directly to this point. HD arrives here, correct? Please come over to this location. If you observe, it's providing a... Take a look at my multimeter situated here in the corner. I will take it from the resistor. Please come over to this other resistor located here. You can't see it in the video, right? But if we follow the trace, you'll see it. With patience, this trace hits the resistor. The opposite side of the resistor. The opposite side of the resistor. It's approaching. Allow me to retrieve it here and check if it proceeds to the microcontroller. Here, it proceeds to the microcontroller on the opposite side of the resistor. So there's the resistor and there's the capacitor here that pulls the reference point. And then the opposite side of the resistor connects to the microcontroller. It subsequently reduces the voltage through these two resistors here. These two resistors draw from the positive terminal, which is in fact the negative terminal. It draws from the positive terminal. This side here reduces the voltage, goes to this resistor here, passes through the resistor and continues over here. Look, there's voltage and the reading is off. Either the resistor has changed, there's a cold solder joint, or this circuit here is also altered. Either the cold solder or the open trace is the change resistor. It's usually the change resistor. Clear, class? We're in this together. Talk too much.